Well, hello and welcome back. We're going to start section 4.3, determining statistical significance. So we just left 4.2, and in 4.2, we started to look at the significance of a p-value. Smaller p-values making something more statistically sound, if you will. Formal decisions. So we're talking now, okay, now it's time to make a decision with the data we have. If the p-value is small, remember small means tiny. We'll talk about tiny. We will reject H of O. That doesn't mean that's the same as accepting something. It means that we have a sample that would be extreme if H of O were true. So we have evidence, we have supporting statistical values that say, hey, I can show you data that says the normal is not normal. These results make this statistically significant, which means that we have evidence in favor of H of O. That's if the p-value is small, okay? If the p-value is not small, we do not reject H of O. The sample would not be extreme. We would not have statistically significant evidence, and therefore our test is inconclusive. Do you like how we do that? So if we're measuring for something and we get a small value, we come out and say, hey, we got evidence that it's happening. My product is a good product. It's really cool. If I don't get the data back, then you know what? The test was inconclusive. I'll get back to you. That's really what happens in statistical measurements. I get some formal decisions here. The formal hypothesis test has only two possibilities. Something happens or something doesn't. The p-value is small. I reject H of O in favor of H of A. I reject H of O in favor of H of A. That's my statement right there. Because I got a small p-value. When I got that small p-value, I like it. The p-value is not small. I do not reject H of O. I do not reject. Okay, now these are statements that we're going to have to go deeper into, because we can't make statements about irrelevance that we don't have information about. The significance level, we are going to call this alpha. This is good old alpha right here. And this alpha symbol is our significance level. At what level of significance are we saying, or what threshold are we using to say that our p-value is small enough to reject the null? Okay, there has to be a standard, if you will, a certain percentile that we have to meet. It says if the p-value is less than alpha, p-value is less than alpha, then we are going to reject H of O. We're going to make it go away. Now remember, our p-value, our percentage, our area will have to be smaller than the alpha number. And the alpha is the threshold. If the p-value is greater than or equal to, so if we have more area, if we have more data, if we have more dots that we have counted, then what it says is extreme, then we're not going to reject H of O. And these keywords are small, not small, how small. So now we have to talk about what that actually looks like. The significance level. If the p-value is less than alpha, the results are statistically significant, and we reject the null hypothesis in favor of the alternative. If the p-value is not less than alpha, the results are not statistically significant, and our test is inconclusive. It says often the alpha level is 0.05 by default. 0.05, which is 5%, right? 5% alpha level, unless otherwise specified. So when we go to the tailing and we look for an alpha characterization, we say, okay, if I can get more extreme or as extreme as this alpha level, if I can get into this 5% area, then I will be able to reject H of O. Big note here. If I do not reject H of O, so let's say my significance level that I receive is not going to break the threshold of alpha, and it's not going to be smaller, I do not reject H of O, but I don't come in and say, I accept H of O. I don't accept that nothing is going on. All I state is that the data that I currently have is inconclusive, and I will continue to look for more data. I do not accept that there's nothing going on. I still want to continue to test and look for not anomalies, but test results which are significant. The lack of evidence against H of O. So I do my test and I can't reject H of O. I don't have something significant. That lack of evidence against H of O is not as the same as evidence for H of O. We don't accept H of O based on the fact that we failed to reject it. For a significance level of alpha at 0.05, so I have a 0.05, which is the standard. What is the decision for a p-value of 0.04? Okay, well, here's what we have to compare. We want to compare our p-value. What we want is our p-value to be less than our alpha. That's what we're really looking for if we are going to accept something. So if I look at this particular one, I have a p-value of 0.004, 4 thousandths. 4 thousandths is clearly smaller than 0.05. I have a significance, or I have data which is less than the significance level. I would reject H of O. For a significance level, again, of 0.05, what's the decision for an alpha level at 0.4? 0.4 is greater than 0.5. I would not reject H of O. I would not accept it, but I would not reject it at the same time. For a significance level of alpha 0.05, what's the decision for a p-value of 1.2? Well, this is kind of a trick question, if you will, if you like that word trick question. Remember, p-values are between 0 and 1 inclusively. Somebody has given us a bogus number. This is not a valid p-value. And it says not valid down here on our choice of selections. So we're not even going to answer whether to reject, fail to reject. And we never, ever, ever accept H of O. So we have a question here, and then this particular question says, numerous studies have shown that fat diets can have a negative effect on a child's health. New studies suggest that high-fat diet early in life might also have a significant effect on memory and spatial ability. In the double-blind study, young rats were randomly assigned to either a high-fat group or a control group. Okay, so somebody's going to get blasted with high fat and somebody's not. After 12 weeks on the diet, the rats were given tests of their spatial memory, and the article states that the spatial memory was significantly impaired. Significantly impaired. That's a big time statement right there. For the high-fat diet rats, okay? So the ones who got a high-fat diet, there was significant results from there. It also tells us that there were no significant differences. I'm going to change colors here. There were no significant differences in the amount of time exploring objects between the two groups. The p-values for the two are, here's one of them, 0.0001 and 0.7. Now remember, that's the area of the test. So I go down and I talk about, okay, which one goes with spatial memory? Okay, so let's go back up to the article and let's read for a second. It says the article states that spatial memory was significant. A p-value which is really, really, really small is a significant measurement. When I go to the next one, it says, hey, what's the p-value that goes with exploring objects? If I go up to the line, it says there were no significant differences in exploring objects. Well, guess what? That one's 0.7. If you found nothing, it's larger than 0.5% standardly. If you found something, it's smaller than 0.5%. It says the title of the article describes a study, high-fat diet causes impaired in spatial memory. In the wording, does this justify for rats? Well, I'd have to say, well, first of all, I look back at the thing and was it a test? Yes, it was a test. Was it blinded? Yes, it was blinded. Did they find significant results for fat? Yes, they did. So yes, there would be a significance because it was an experimental study. Statistical conclusions. So let's look at these. So when we're making these choices and we're trying to make a decision based on something, first of all, when I talk about the statistical conclusion, to reject H of O, I have to be something smaller than 0.5%. That's if we're actually on a 5% alpha. Alpha can change, so let's not assume that alpha is always 5%, but most of the time it is. So numbers up to 5% are going to be rejection time. Anything over 5% is not a rejection. The further you get away from rejecting, the greater you become at or the greater you feel good about rejecting something. In other words, if this is my norm right here, the further I get away this way, in other words, the smaller the p-value, the greater or the more strongly I feel about the evidence to reject H of O. The smaller the p-value, the more strongly I feel comfortable rejecting H of O. This is from the formal decisions based on an alpha level at 0.5%, or excuse me, a 0.05. Question number 19 here. It says that it is believed that sunlight offers some protection against multiple sclerosis, but the reason is unknown. All mice were injected with proteins known to induce a mouse form of MS, and they observed which ones got MS. Researchers randomly assigned mice to either one of the groups, a control group, nothing going on, or one that got a vitamin D supplement and a UV light. First question is the study is, and it's asking us what kind of study this is. Well, this is definitely an experimental study, right? So this is an experimental value. It's not an observation. The scientists found that mice exposed to the UV light were significantly less likely to get MS. There's that word, significantly less. But the vitamin D did not seem to reduce the likelihood. One p-value was 0.472 and the other value was 0.002. In testing whether the UV light protection against MS, the p-value is, okay, so I go up to the one that says MS, and it says MS was significant, right here, significant. Well, if my two choices are 0.472 and 0.002, then if I just found significant data, it's 0.002, because notice that number is smaller than an alpha level of 5%. In testing about the vitamin D protection against MS, the p-value would be the other 0.472. You have found nothing when you found 0.472, which means you did not reject H of O. Wow, this is a bunch of wording right here. Let's see what we got. Could owning a cat as a child be related to mental illness later in life? Toxoplasmosis is a disease which is transmitted primarily through contact with cat feces. Yuck. And has recently been linked with schizophrenia and other mental illnesses. Also, people infected with toxoplasmosis tend to like cats more and are 2.5 times more likely to get in a car accident. Okay, well, due to delayed reaction times. Wow. Okay, so owning a cat and having this toxoplasmosis, I'm 2.5 more times likely that I'm going to crash. Couldn't be from texting and drinking iced tea and things like that. Due to delayed reaction times, the CDC estimates that about 22.5% of Americans are infected with toxoplasmosis, and most have no symptoms. Oh, what does that sound like today, right? And this prevalence can be as high as 95% in other parts of the world. A study randomly selected 262 people registered with the National Alliance for Mental Illness, almost all of whom has schizophrenia. And for each person selected, chose two people from the family without mental illness who were the same age, sex, and socioeconomic status. Each participant was asked whether or not they owned a cat The results showed that 136 of 262, okay, well, there's a data point right there. 136 out of 262 people in the mental ill group, the mental ill group had owned a cat, while 220, probably need another color here, while 220 of the people in the not mental ill group had owned a cat. For this study, calculate the relevant difference in proportions of cases for those with schizophrenia who owned a cat minus the proportion of control who owned a cat as a child. Okay, so what we need to find is P1 and P2. All right, so let me change colors here. So my first control group, I have 262 P1. Let's call P1 is my mental ill group, own the cat. 136 of them out of 262. Those are the number who were in that group. When I go to my P2, 522, 220 out of 522. So P2 is equal to 220 out of 522. Our statistic down here wants us to take 136 out of 262 and subtract, in that order, 220 out of 522. Jump to your calculator, put those fractions in, and it should deliver to you a 0.098. Make sure you're using your fraction key, getting to that value right there. Let me jump to the next slide. For testing the hypothesis that the portion of cat owners is higher in schizophrenia group than in the control group, use technology to generate a randomized distribution and calculate the p-value. Okay? Then I'm going to have to take a moment and we're going to have to put some stuff into the calculator. So give me 1 second. I'm going to turn off the computer for a moment. I'm going to go get set up, and then I'm going to come back to you, and we're going to take care of this. 1 moment, please. Okay, I'm back, and I have my stat key opened. Took me a moment. So first of all, a couple of things that we have to judge. So we're talking about, if nothing is going on, then, and I'm going to write this on the board real fast. If nothing is going on, then P1 is equal to P2. Okay, so our H sub O is that if nothing is truly happening, then P1, proportion of the first group, is equal to the proportion of the second group. I, again, should have a colon there. If something statistically is going on, then H of A, then remember, we want the first group to be greater than the second group. Okay? Want the first group to be greater than the second group because we're looking for statistical significance between the two. All right, I'm going to erase this so we can actually run this stat. So the first thing we have to do is we have to take those two fractions that we created for those two groups, and we have to put them into StatKey. Now, let me back up a little bit where I am. So in StatKey, first of all, I'll go back to the main page. I'm over here on the right, randomize hypothesis, test for different proportions, edit the data. Let's put in the numbers that we have. So our first one was 136 out of 262. Our second group was 220 out of 522. Say okay. Notice it sets up the null hypothesis nicely. I'm going to generate 1,000 samples. Cool. I got a little curve right here. Notice the null hypothesis is set up at 0. That's where it should be. Remember, I just said I want P1 to be greater than P2. So I'm going to make this a right side tail. I'm interested in data values that are greater than P1 minus P2. Now, remember, when we took the math and we subtracted P1 minus P2, our statistic was 0.098, not 0.069. So what we want to measure is, okay, on this curve, if this data point down here were 0.098, what's the p-value going to be? Let's click on this. Let's make it 0.098. We're putting in our statistic. We're hitting OK. And look what just happened to the p-value. We now have a p-value of 0.001. That thing is incredibly small. Again, I changed my data point to 0.098 because that was my data point. From that data point, I found that I had a p-value incredibly smaller than 0.05. So in my mind, at this point in time, I have significant evidence. I am going to reject the null hypothesis in favor of the alternative because I only have a 0.001 chance of this actually happening. We're going to go back to here, and we're going to pick back up from the current slide. The question is, what was the p-value? Well, I got a 0.001. Now, if you run it, you may get a 0.002. A 0.001, a 0.002, a 0.003, they're all smaller than, and I'll write that up here, they are all smaller than a significance level of 0.05, okay? This is the p-value, and this is the alpha. Remember, we want the p-value to be smaller than the alpha if we decide to do a rejection. So the question is, do you think that owning this, is there an association? Now, remember, we never do causation, but we can definitely talk about association. And absolutely, I think that is. The answer is yes. You did a study, and in that study, you found significant evidence. Summary. Results are statistically significant if the p-value is less than the significance level alpha. In making a formal decision, we reject H of O if the p-value is less than alpha. Otherwise, we do not reject H of O. Not rejecting H of O is not the same as accepting H of O. Have a great day, and I will see you on the next section.